So what is K-means clustering? You are given a set of documents and you are given a number k. This is the number of clusters you want to have at the end. And you want to partition this set of documents into these k clusters. So what is a partition? A partition is a partition of a set is a, you can say, a dividing up of the set into k clusters such that each member of the set belongs to exactly one cluster and every member is classified into some cluster. There's no member that's left out. Now, what would be a good way to partition the documents into these k clusters? Well, if we want to come up with an optimal clustering algorithm, we could define some kind of a mathematical objective function. For example, we could define a function which measures how similar the documents within each cluster are, add up the similarities of documents between within each of the k clusters, and then try to minimize that sum. Okay, or try to minimize the, so let's say I compute the distance between pairs of documents within every cluster, and I compute what the uh, average average distance between documents within the same cluster is. So that's one measure I could try to optimize, or I could try to optimize the sum of the values of the uh, distances between pairs of documents that belong to the same cluster. But anyway, however you define this objective function, it's very hard to mathematically optimize, to come up with a mathematically optimal solution, because the time that you will take, that your algorithm will take to explore all possible partitions and to identify the partition which optimizes that objective function, that time is going to be very huge. So what we'll be doing is we'll be looking more at heuristic methods. Heuristic methods are not guaranteed to be optimal, but they run pretty fast. That's why we use heuristics. So k-means clustering is going to be an example of a heuristic method for clustering. And actually the best way to look at it is via an example. I'll just come to that. Recall that our documents are going to be real valued vectors of something like df/idf weights. And then we're going to have the notion of a centroid of a cluster. So the centroid of the cluster is, or the center of gravity of a cluster is just the mean of all the vectors for documents in that cluster. Okay, so just take the vectors that lie in that cluster and then just take the average of all those vectors. That's the centroid or the center of gravity. So how exactly does k-mean clustering work? Well, let's look at this example. Um, so can you see this slide in full screen mode?
Yes, sir.
Okay. So here's an example of k-means clustering. So we are given that k is equal to 2. So we want to divide all these points into two clusters. And from your naked eye, you can easily figure out what these two clusters should be. It should be these two. But how do we do that using k-means clustering? Well, what we will do is we will start off by picking two seeds. Okay, so for each of these k clusters, we will choose we will choose k documents out of the collection and treat each of them as a seed for one particular cluster. So you can see that one of the documents is colored red and the other one is colored blue. So these are the two seeds that we have picked. So these are, by the way, like leaders. If you want to, compare this with cluster pruning that we did earlier, these are like the leaders. And then each of the other documents are going to be colored red or blue depending on whether they are closer to the red seed or to the blue seed. Could you turn off the microphone, please? I'm hearing an echo. So you can see that all the points that were closer to the red seed have been colored as red, and all the points that are closer to the blue seed have been colored as blue. So this is the initial random uh, cluster that we start off with, and we are going to refine these two clusters so that at the end we have two meaningful clusters. So this is what these two clusters start off looking like. Now what we will do in each step of the algorithm is we will compute the centroid of the current clusters. Okay, so this red X is the centroid of all the red points, and this blue X is the centroid of all the blue points. Then what we will do is each of these documents will potentially change its cluster depending on whether it's closer to this centroid or to that centroid. Okay, so we will reassign the clusters now. Each document will be assigned the cluster to which this document is closer. Okay, so all these documents were closer to this particular um, centroid, this blue centroid, and so they've been colored blue. Recall that in the previous step these three documents were colored red, but because they are closer to this blue X than to this red X, they will change their identification and become blue. And likewise all these red points, because they are closer to this centroid, they will become red. Now once you reassign the cluster, again you will compute the centroid of the new clusters. And these are the two centroids now of the new clustering. And again we'll do the same thing. For every document we will see whether it's closer to the blue centroid or to the red centroid, and depending on that the, the document can switch its cluster. But it turns out that these documents are already close to this blue centroid. These documents are already close to the red centroid. In fact, none of the documents here change their identity. So clearly, if we compute the centroid again, they will be identical to the present centroid, because the present centroid was computed based on the same cluster, the same set of documents in each cluster. So our algorithm has therefore converged, and we have these two clusters at the end, exactly the two clusters that you would have come up with your naked eye. Any questions about how K-means works? Let me describe this uh, in a more textual way. What we do is we select k random documents as seeds. So we want to have k clusters at the end. The number k is given to us. So we start off with k documents as seeds, and then all the other documents are mapped to one of these k clusters depending on which of the k seeds they are closest to. Okay, so that's the initial clustering we start off with. Then what we do is we compute the centroid of each of these k clusters, and once we compute the centroid, then we look at each document and then compute the centroid to which each of the documents is closest to, and depending on which of the k centroids each document is closest to, it can change its cluster identity. Okay, once we do this for all documents, again we'll compute the centroids of the k new clusters, and then go back and again compute the again compute for every document which is the closest centroid, and then we'll keep on iterating like this until the algorithm converges. Any
So,
questions about this? Yeah.
so why does this approach work, sir? Like, I mean, why should it converge at all? Like,
Yeah, I'll
if it,
I'll I'll explain that in a few slides. So just hold on to that question. Any other questions? Okay, so reassignment of documents to clusters is based on the distance to the current cluster centroids. Okay, so now you can see why we're talking about distance instead of similarity, because it's easier to think of distances visually. Okay, so what are the conditions uh, under which, I mean, what is the termination condition for this algorithm? When do we stop? Well, we could stop after a fixed number of iterations, whether or not we converge after those number of iterations. That's one of the ways. In fact, it turns out that K-means clustering converges pretty fast, so we could predefine a fixed number of iterations, and after those number of iterations, whatever are the clusters, we can say, well, these are the clusters that we have. Or we can stop when the partitioning of the documents is unchanged. Okay, just like we did for the example we saw. Or we can stop when the centroid positions don't change. Okay, and obviously if the document partition is unchanged, then the centroid positions also will not change. So coming to that question, why should the K-means algorithm ever converge? Okay, that is, why would we arrive at a set of clusters which won't change after beyond that point? Now, K-means algorithm is a special case of a more general algorithm called an expectation maximization algorithm, often abbreviated as an EM algorithm. And if you look at the expectation maximization algorithm in general, it's known to converge, even though the number of iterations after which it converges could be large in theory, even though in practice it's not usually large, because the expectation maximization algorithm converges. K-means, which is a special case of that, will also converge. But of course, this may not be a satisfactory answer to you, because you may not know what an expectation maximization algorithm is and why that should converge. So let's try to independently argue why the K-means algorithm will converge. So let's define the goodness measure of a cluster as the sum of the squared of the distances of all documents in that cluster from the cluster centroid. Okay, so what we are doing here is, if we have a particular cluster of documents, okay, let's say this is one cluster, and we have a centroid. Here's one question: what is the average of the distances between each document to the centroid? Sorry, that is, if we were to take the each document vector in this cluster, and the vector from that document to the centroid would be d minus x. I mean, doesn't matter whether the vector is going from here to here or there to here. The magnitude of the vector will be the same. But what if we add up all these over all the documents in the cluster? What will be the result?
So would it be 0, sir?
Yeah, it will be 0, because by definition the centroid is the mean of all the vectors in the collection, right? So if I take the difference between each of the vectors and the centroid and add them up, that will be 0, because by definition this centroid is the summation of all the documents in that cluster divided by the number of documents. So instead of looking at that, so recall, if you've done a basic course in statistics, you know that if you take a bunch of points and you have a mean for those points, and if you take the difference between the um, each of the points and the mean and then add them up, the result will be 0. But there's something called standard deviation, where instead of adding up the difference between the of each a point and the mean, you take the square of the, so that this result will be positive now. And so this summation will not be 0, because even if this difference is negative, the result will be positive. I'm talking about numbers here. Obviously for vectors, what will be the uh, instead of d minus x square, we will be measuring effectively the square of the length of the vector. So let's go back to the slide. That's what we are doing here. We are kind of taking the variance. Okay, so standard deviation is obviously the square root of the variance, but this is analogous to the variance of a set of data points. So this is the mean of the data points, and from each data point we are subtracting the mean and then squaring up. So di minus ck square is a measure of how far di is from the centroid, how far document I is from the centroid. And we are adding up these squares of the distances for each document in the cluster. And we do this for every cluster. Okay, we compute this measure for every cluster and then we add up those measures. And we call the overall sum as G. Now here's the claim. The claim is that every iteration of K-means algorithm will go on decreasing G. So if we can prove that every iteration of the algorithm will go on decreasing G, the algorithm has to converge because G cannot be reduced indefinitely. Okay, sooner or later you will have to uh, basically hit some value beyond which you can't go further. So is that clear? So we're going to try and prove that in every iteration of the K-means algorithm, the value of this G can only go down. It cannot increase at ever. It will always decrease. And by showing that, we will be showing that the K-means algorithm converges because G monotonically decreases and it cannot decrease indefinitely. Now there are two things we do. Let's go back to the algorithm itself. So before the break, we were trying to look at a measure which we called as G, capital G, that we claimed as a measure that will go on decreasing with each iteration of the K-means algorithm. So let's look at uh, the example that we went through and see and try to argue that G will actually will actually go down with every iteration of the algorithm. So how did we start the algorithm? We started with, because we had k equal to 2, we had to choose two random documents as the seeds, and then we had to compute the distance between all the other documents and these two, and depending on whether the red dot was closer to each document or the blue dot, the color of all of these black documents would become either red or blue. Now at this stage, what is the value of G? How would you compute G? So how many red dots are there? Let's say I call these as D1, D2, D3, D4, D5, D6. Okay, there are 6 documents here and there are 6 over here. So let's say I call these as D1 to D6 and these as D7 to D12. If for some reason PowerPoint is not allowing me to use the pen option, so just imagine labeling these from 1 to 6 and these from 7 to 12, and let's label these 3 as 7, 8 and 9 and these as 10, 11 and 12. Now to compute G, we have to compute the distance. So D1 to D9 are the red dots and D10 to D12 are the blue dots. So what would be G here? G would be, for the red cluster, it would be document di minus the x red okay, where I varies from 1 to 9. And for the blue cluster, it would be the distance between each of the documents in the blue cluster to the blue centroid, right? Any questions about this? So effectively there are 12 terms that we are adding, one for each document, and we are saying that the sum of these 12 terms is what we want to claim as G. And of course these 12 terms can be divided into two clusters, okay, corresponding to the clusters into which the documents are present, okay, because 9 of these documents are in the red cluster, so the centroid for 9 of them will be the red centroid, and the centroid for the other 3 will be the blue centroid. Is that clear? Now let me ask this question. Let's go back to, so here's the question. What is the point for so this the coordinate of this, let's just focus on the red cluster, okay, and we are looking at the centroid here. Now here's my question: what should be the coordinate of x red? Forget for a moment that this is the centroid, okay, forget about the fact that this is the centroid. Let's say any arbitrary point P. If I were to compute the sum of the squares of the distances between all the red points and an arbitrary point P. Okay, so P could be the centroid, it could be located here, it could have been located here, it could have been located here, it could have been located here. Where should P be located so that this will be minimized? Sorry, this. Again, this is basic statistics, or if you don't remember your statistics, basic calculus. So the coordinates of uh, all the 9 points are constants, okay, they are known to you, but you don't know what the coordinates of P are. Basically you want to derive the coordinates of P by trying to minimize this function. And obviously P is a v-dimensional vector, so if you're getting confused about the vector itself, note that um, each individual term, so let's say we look at document D1, okay, for D1 this value is going to be, so let's say P is a v-dimensional vector, P1 P2 till PV, okay, and D1 is also a v-dimensional vector, D11, D12, D13 and so on up till D1V. So when we say D1 minus P squared, actually strictly speaking what we are doing is we are taking the L2 norm and squaring it. So basically we're trying to compute the variance. So that would be P1 minus D11 square plus P2 minus D12 squared plus so on up till PV minus D1V square. Okay. Now P1, P2 and so on till PV are constants, whereas these values, oh sorry, D11, D12, D1V, these are constants known to you, whereas P is what you want to compute. Okay, so these are variables, but these are independent variables because this corresponds to the coordinate along one of the axis, the other corresponds to a coordinate along the other axis, and so on. So you can independently minimize, compute what the minimum value of what value of P1 will minimize this component of the. Of course, this is not the only term here. You'll have for D2 you will have similar other terms. For D3 you will have V other terms, and effectively you're adding all of them, and you're asking what should be the coordinate of V such that this whole sum will be minimized. What will be the answer? Suppose I have, let's just remember your basic calculus. Suppose I have this function x minus 2 squared plus x minus 4 squared plus x minus 6 squared. Okay, so let's say this is the function f of x. What will minimize, what should the value of x be so that this is minimized? How do you compute that?
So we'll have to take the derivative of f of x
Yeah,
and like find the minimum of using like the point at which f of x changes sign. Over there we'll know that from negative to positive that will be a local minimum, and we can identify the local minima and then
yeah,
do it.
yeah. So the derivative of f of x will be twice of x minus 2 plus twice of x minus 4 plus twice of x minus 6, and this derivative, so what is the derivative of a function? It's basically the slope of the function at that particular point, right? So the place where the function reaches a local minimum, that is the place where the derivative will be zero, either a local minimum or a local maximum. It could be either. But because this is a quadratic function in x with a positive coefficient of x square, the shape of the function will be a parabola opening upwards. Okay, this is again from your algebra. If you recall your quadratic equations from high school, we have ax square plus bx plus c where the coefficient a is greater than 0, then the shape of this is going to be a parabola opening upwards. Okay, it could be like this, it could be like this, it could just touch the x-axis depending on how many roots this equation has. So this is going to be a parabola opening upwards, and so the derivative will be 0 only when the function is minimized. Okay, at this particular value or this particular value or this particular value. It's not going to be a local maximum, it's going to be a local minimum. So if I equate the derivative to 0, this 2 can obviously be cancelled off. I'll get x is equal to, sorry, 3x is equal to 2 plus 4 plus 6, and so x is 2 plus 4 plus 6 divided by 3. Basically x is the average of these three. Okay, so the value of x which minimizes this function is the average of these three. So this is analogous to our example, because this is just a one-dimensional example. So if you look at the number line, you have 2, 4, and 6. And basically I'm asking you where should x be placed along this number line so that this particular function is minimized. This is like the g. Okay, except that we're talking about g in a v-dimensional space instead of along a single dimension. Okay, so where should x be placed so that this is minimized? Well, the average of 2, 4, and 6 6 plus 4 is 10, 10 plus 2 is 12, 12 by 3 is 4. So x should be placed exactly here. That is when this will be minimized. Now you could have extended this to two dimensions. Okay, so I could have had a function of two variables, f of x comma y, and I could have had, so I could have said my data points are, let's say, 9 in number. Okay, and I want to identify I want to identify a point x or whatever, I mean by this cross, such that the sum of the square root of the distances between all these points to this to this particular point is minimized. Okay, so if one of the points was x1 comma y1, if the other one was x2 comma y2, x3 comma y3. Okay, so the value that I'm computing, so the value would be x1 minus, so let's say this coordinate is um, actually let me call these as a1 and b1. So a1 comma b1 is, because a and b are constants which are known to you. So this is a1 comma b1, this is a2 comma b2, this is a3 comma b3, and this is x comma y. Okay. So this function of x and y will be x1 minus a1 squared plus y1 minus b1 squared plus x2 minus a2 squared plus y2 minus b2 squared. Okay, this is the sum of the square root of the distance between x comma y, this point, and a1 comma b1. This the sum of the, sorry, the square of the length of this particular line segment. The second term is the sum of the square root of this particular line segment, and likewise a3 comma b3 and so on. So uh, how do you minimize this function? Sorry, this is x and y. X1 comma y1. This is just x and y. X minus a9 squared plus y minus b9 squared. So what will be the values of x and y that minimize this function?
Sir, at x equal to a1 plus a2 plus 1 up till a9 divided by 9,
Mm-hmm.
and y equal to b1 plus b2 so up till b9 divided by 9,
Yeah,
or like the means of ai and bi.
yeah. So if I take the partial derivative of this function with respect to x and I set it to 0, I'll get the value of x to be equal to the mean of the a's. And if I set the partial derivative of this with respect to y to be equal to 0, just like we were doing earlier, except that we were doing it in one dimension, now we have to set both the partial derivatives to 0. And of course this is a three-dimensional, this is a two-dimensional function, so the way to think of this function is more like a, um, instead of a parabola, this is more like a paraboloid. Okay, it's like a cup, and there is a well-defined bottommost point for that cup. Basically, we're just extending this to higher dimensions. So if you do that, then x here will be the average of the a's and y will be the average of the b's. And this is precisely how we defined the the centroid of a bunch of points. Okay, the centroid is just the average of the individual coordinates in all the dimensions. This is in two dimensions, but now we can extrapolate this to a v-dimensional space where you can think of these two coordinates a and b as representing a vector of length 2. So we have v coordinates instead of two coordinates. And so the value where this kind of a function extrapolated to v dimensions will be minimized is at the centroid of all the points. Is that clear now? The proof will be just a simple extension of this. Any questions about this? So coming back to that, to the question I asked you, what will be, what should be the coordinate of a point P such that the distance, the square of the distance from all the 9 red points in our, so where should this x be placed so that the sum of the squared of all these, of all the distances of all the points from x is minimized? What's the answer now?
The centroid, sir.
Yeah, the centroid of the 9 points. Now, is this particular point the centroid of the 9 points?
Yes, sir.
It is, right? It is the centroid of the 9 points. So, this is the point where the value of g1 and g2. Okay, so let's define g1 to be the value of the component of g coming from the red cluster, and g2 to be the portion of the portion of g that is coming from the blue cluster. G is just g1 plus g2, or you can say g red plus g blue. Now what do we do in the next step? We recompute the distance between each of the points and these two centroids. Okay, and now you can see that these 3 red points in the next step change their color to blue. Now let me ask you this question. Here, these 3 red points, if you look at the sum g, okay, there were 3 terms that were coming because of these 3 red points. What were the 3 terms? The coordinate of this point minus this coordinate squared, plus the coordinate of this point minus this coordinate squared, and the coordinate of this point minus this coordinate squared. Okay, so those were the 3 terms which were made up by these 3 points. Now if I look at the sum of those 3 terms, okay, so if this is d7, d8 and d9, let's look at d7 minus um, x red squared plus d8 minus x red squared plus d9 minus x red squared. And let's look at the same thing with respect to the blue cluster. Now can you tell me which of these two is the smaller?
So the blue one.
This is smaller, right? Because this value is smaller than this value. That is why D7 changed its color from red to blue, because it found that the blue centroid was closer to it than the red centroid. Right? This point found that the blue centroid is closer to it than the red centroid, so it changed its color to blue. This point also found that the blue centroid was closer to it than the red centroid, and so it also changed its color to blue, and that's why this one also changed. Now, what happened to the value of of G? Sorry, let me call that the value of G before this change of color as G before and G after. What changed in the so how did G change before and after this transition? Recall that G had how many terms? 12 terms, right? Corresponding to all the 12 points. Before this transition, 9 of those points were colored red, 3 of them were colored blue. After the transition, 6 of them were colored red and 6 of them were colored blue. So for 9 of the points, the terms that they make up in G did not change because their colors remained the same and the location of the centroids is the same. Okay, the location of the centroids is the same and the colors are the same. So those 9 terms will remain the same, and the remaining 3 terms changed. Okay, this term became this term, this term became this term, and this term became this term, and the remaining 9 terms remained the same because their colors did not change. Is that clear? So my claim is that G after is going to be less than G before, after this step. That is, if we compute the average distance between all the points and the centroid, that average is gone down. Strictly speaking, it's not the average, but the squared of the distance. But you get the point, right? Is that clear?
Yes, sir.
Okay. Now here's another point to note. So that this was one of the moves that we make in every iteration. The second thing that we do in each iteration is we recompute these two centroids, right? Right now, is X the centroid of these 6 points? No, X was the centroid of the 9 points, right? X was the centroid of these 9 dots. This blue X was the centroid of these 3 blue dots. Now after these 3 changed their color to blue, we said that the value of G has gone down. Okay. The next thing that we do is we recompute this red X point and the red blue point. We recompute the two centroids. Now let me ask you this question. This, before we recompute the centroid, that is at this particular snapshot of the picture, what is the value of G? It has 12 terms again. The six of those terms are measuring the distance between these 6 red points to this X. The other 6 terms are measuring the distance between these 6 blue points to this blue X. Now again, let me ask that question. Where should this blue X be present so as to minimize the average distance between the 6 points and that X? Okay, where should that X be placed in this space?
At the centroid, sir.
At the centroid. And right now X is not at the centroid. Okay, this X was the centroid of the previous blue cluster, the blue cluster from the previous step. So if we recompute X, okay, if we recompute the centroid, it moves from here to here. Now in moving from here to here, what happened to the sum of the 6 terms that we had? So the 6 terms we had at this stage, sorry, the 6 terms we had at this stage and the 6 terms that we will now have after this transition of X. Which of those two will be smaller?
So the one after the centroid,
Yeah,
because
because that is the one that minimizes that function, right? The function of, uh, I mean, the sum of those 6 terms. Similarly for the red centroid, before it was present over here, and after recomputation of the centroid, now it's present at the actual centroid of these 6 points. So now it's minimizing the sum of those 6 terms over here. So again, so this was, what did we conclude here? After the change of color, G goes down. Okay, that is, the points which change their color will contribute to the lowering of G. Okay, now we are saying, and after the recomputation of centroid, after the recomputation of the centroid of the new centroids, G further goes down. Okay, so in both these steps, the value of G after is less than the value of G before. And these are the steps that we are repeating again and again in every iteration of k-means. So we have proven that in every iteration of the k-means algorithm, the value of G will keep going down. Is that clear now?
Yes, sir. Yes, sir.
Now, is this algorithm guaranteed to, so is the value of G at the very end when this algorithm converges guaranteed to be the optimal value? I mean, you've shown that it's converged, but is it guaranteed to be the optimal? What do I mean by the optimal? The value, uh, the least possible value. Actually, if you go back to that slide which we saw here, okay, we said that we can define some kind of an objective function that we want to minimize, and that objective function, as you can see now, is G. Okay, so if we have k clusters, we can define what G is. G will be the sum of the squared of the distances between every document and the centroid of the cluster to which that document belongs. And the globally optimal clustering will be that particular partitioning of the documents into these k clusters for which the value of G is minimum. Now my question is k-means going to yield at the when it converges, is it going to converge at that optimal value of G? What do you think? I actually told you the answer when I covered this slide, but I'm revisiting this slide because now you understand better what that objective function is.
So I think yes, it should come to the globally active optimal because it at every iteration it's going to become better. So that's why I was thinking that.
Okay. So imagine this scenario. You are a traveler. Okay, you're hiking along a set of hills. Okay, and what you decide to do is at each step you decide to climb one step down from where you are. Okay, so in each step you will descend in some particular direction. So you will see relative to where you are, what is the next step that you can take which will be lower than the elevation at which you are currently are, and you will take that next step. Then from that next step you will again look around you, see in which direction you should take a step so that you again further go down. If by following this procedure, are you guaranteed to reach the lowest elevation? Let's say there is a bunch there are a number of valleys in that particular hillside. Are you guaranteed to reach the deepest valley, the bottom of the deepest valley in this particular way?
No, so it would depend on the initial path itself, like
Yeah,
where we
exactly.
went.
So it depends on where you were initially. It's possible that it's possible that you may find yourself at the bottom of some other valley, at the bottom of some local minimum valley. Okay, so in your hillside there would be one valley whose depth is the highest. There could be other valleys that are not so deep. By following this procedure, you are guaranteed to reach the bottom of some valley, but that may not be the deepest valley. In a similar way, a heuristic algorithm is not guaranteed to converge at the optimal solution, but it will be some local minimum solution. Okay, and if it's a good heuristic, that local minimum may frequently be the optimal as well, but it's not guaranteed theoretically. to be the optimal. So that is something you can again see through this particular example. Recall that k-means starts by assigning, taking two of the documents, assigning one of them the color red and the other one the color blue. Right? So suppose we had started with this as the red document, this as the blue. What would have been the result? What would have been our two clusters? If this is red, then this document is closer to this document than to this document. Right? So this would have been become red also. Likewise, this document would have been closer to this red seed than to the blue seed. So this would have become red. So these three would have been red, and by the same reasoning, these three would have been blue because D and F are closer to E than they are to the blue seed B. So you would have had this as red, this as blue. And then you would have computed the centroid. The centroid would have been somewhere along this same line. Okay, and the centroid here also would have been somewhere along the same line. In fact, they would have been, sorry, by the nature of this figure, they would have been exactly one below the other. Would that have, then in the next step, would your clusters have changed? No, they would have remained the same because the points along this line would have been closer to this particular centroid than to the other centroid. So your algorithm would have converged with the clusters A, B, C, and D, E, F. But suppose you had started in a different way. Let's say you had assigned this to be the red seed and this one to be the blue seed. Then your clusters would have been, you know, uh, this would have been the red cluster when you converge, and this would have been the blue cluster. Do you see how? Because these 3 points would have been closer to this seed, so this would have become one cluster. This point would have been closer to this seed, so this would have been the other cluster. And when you compute the center of gravity, one of them would have fallen here, the other one would have fallen here. And then the documents in one of the clusters, in this red cluster, would have continued to be closer to this centroid than to the other centroid, and vice versa. So you can see that depending on where you start, your solutions or your clusters could be different at the end. So some seeds can result in a suboptimal clustering. It's also possible that the convergence rate could be different depending on how you seed at the beginning. So you may require a larger number of iterations to converge with some seed select with a particular kind of seed selection. Okay, what would be the time complexity of the algorithm? So let's say that the length of the vectors is m. Actually, it's v. V is the size of the vocabulary that we saw. So let's take it as m here. Computing the distance between two documents is order m time, right? Because you have to compute the difference between each of the components, take their squares and add them up, and then that would be the squared of the distance, and that would be order m. Assigning Reassigning clusters would take time order k times n. Why? Because each document would be potentially reassigned. So each document will compute its distance to all the k clusters or all the k centroids. And computing one single distance takes time order m that we just saw. And how many distances will it need to compute? K times n. Right? Because for each of the n documents, you are computing the distance to all the centroids, and there are k centroids. So there will be n documents, each computing distances to k centroids. So there will be k n distance computations, and each distance computation takes time O of m. So the total time will be O of k and m. And then computing the centroids, uh, how much time will it take to compute each of the centroids once the colors have changed? Well, each document will be considered exactly once in the computation of some centroid. And the way it will be considered is it will be added to the other terms for that centroid. And every time a document is added to some other, existing sum, the time taken will be big O of m, time to add two vectors. And since each document is going to get added once, so the total time will be n times m, because there are n documents and each of them will be added once to some centroid, and when they are added the time is O of m. And there are I iterations, so these two steps will have to be done I times. So the total, because this one is the larger among these two, the time complexity of a single iteration is dominated by uh, this particular expression. And so I times this particular expression will be the total time complexity of K-means clustering. Any questions?
No, sir.
Um, so we have assumed so far that the value of K is given to you in advance. So we are partitioning the n documents into a predetermined number of clusters. What if K is not given to you in advance? How do you find the right number of clusters? This is a very hard question. What we do is we usually uh, try different approaches. So we try different values of K. For some values of K, we may end up getting clusters that are very, very imbalanced. Okay, some clusters may have a huge number of documents, others may have very few. And so then we can decide to increase the value of K and then try the algorithm again. Or we can do something like this. What do you think will be the value of G if we had started with a larger value of K? So let's take as the trivial clustering example we saw. Each document belongs to its own cluster. What is the value of G in such a clustering algorithm?
It will be 0, sir.
Yeah, it will be 0 because each cluster has a single document. So the centroid of that cluster is the document itself. And so the distance between each of the documents to its centroid is 0. And so all the terms are 0, and so G would be 0. So if we had to just minimize G, we could do it easily by increasing the value of K. Okay, for K means we could not vary the value of K because it was given to us in advance. But suppose we were allowed to vary the value of K as well. Then what would we do? We could do something like this. We could take G and add to it a negative cost corresponding to how many clusters there are. A negative cost corresponding to how large the value of K is. Okay, so we have two terms now. We have the benefit term, which is the G term. Okay, the benefit term will measure how small G is, and it will be larger if the value of G is smaller. So as I mentioned, distance and similarity are the inverse of one another. So when we think about benefit, you can think of benefit being larger when the similarity is larger. When the similarity of documents in a cluster is larger, which means when the distance is smaller. When G is smaller, the total benefit is larger. And the cost here is, so we want to penalize having a larger number of clusters. Okay, if we have only a single cluster, then the value of the benefit will be small because the value of G will be large. So that is one extreme. The other extreme is if we have n clusters. In that case, the benefit will be very high because the value of G will be 0. But the cost will now be high because this cost is proportional to k. Okay, so if the cost of a single cluster is c, the cost of k clusters will be k times c. So we have a trade-off now. We want to, we'll be avoiding both extremes, because if we have this kind of a function which takes into account both the benefit and the cost, then we won't go to the extreme of increasing the number of clusters to n, nor will we end up with a simplistic scenario where we just have a single cluster for all the documents. Is that clear? That's something we could try to do. This is some kind of an objective function which we could try to minimize. One last thing I'll probably mention here is, notice that this kind of a clustering algorithm works well for the vector space model that we've talked about, but it may not work well in other scenarios. For example, let's say you were given, outside of web data mining, let's say you were given the coordinates of all the volcanoes along the surface of the earth, and you had to cluster volcanoes into different clusters corresponding to how close the volcanoes are to one another. Then it's possible that if you take something like the Pacific Ring of Fire, where you have a large chain of volcanoes potentially very far apart from one another, they won't be linked together necessarily by this method, because in vector space scoring, your distances are being measured. So from a particular point, the distances in all directions are the same. Whereas if you look at something like a volcanic chain, okay, volcanoes that are part of the same fault, which are present along the same edge of the continent, they will be logically grouped together in the same cluster. Semantically, they are more similar to one another than volcanoes somewhere else on the continent. Okay, so for clusters that are spherical in vector space, k-means works well, but it may not work well in for other kinds of data. And secondly, outliers may belong to the result in their own clusters. What is an outlier? An outlier is a data point that is very far apart. Okay, it's like an abnormal point which has some abnormally high or low values for the coordinates. It's present far away from the rest of the points. So how do we deal with outliers? If you don't deal with outliers, then the outliers will lie in their own cluster. Right? But we may want to eliminate outliers. Okay, so k-means by itself does not do any outlier filtering, but we can add that notion. It's disjoint and exhaustive in that each document belongs to exactly one cluster, so it's disjoint, and it's exhaustive in that each document belongs to some cluster. There is no document that is unclassified. Okay, so I think we're out of time. We'll look at hierarchical clustering in the next lecture. Do you have any questions based on today's material?
No, sir.
Okay, so we can stop.
Thank you, sir.
Yeah.
Thank you, sir.